Okay, so let's continue with our overview of the computer system structure, right? So if you look into a computer, right, a computer system operation, basically, today's computer at least, in most of the cases today, right, there exists at least one CPU, two CPU, or multi-core CPUs, right? And it's connected to a disk controller or some kind of controllers, right? Device controllers. So it can be a disk controller, USB controller, graphic adapter, or other kinds of controllers, right? That would help interface other devices, right? Disk, mouse, keyboard, printers, monitors, and all of this is basically connected, right? Through a system bus, right? Where they would allow access to a shared memory somewhere on the computer, and where we have the memory on the computer, right? So, mm, so if you look into these kind of systems today, the CPU and multi-core CPUs, that is, this controller, USB controller, graphic adapter are all competing, basically trying to access memory on the and transfer data through the system bus, right? So it has to be managed in a way, and we'll see how these things kind of work together, right? Computer system operations, I/O devices, and the CPU can execute basically concurrently. So in this picture you see all of this. Sometimes while the CPU is doing computation, the disk controller is basically reading hard disk. The mouse, keyboard, and printer is basically keyboard is probably reading whatever key that you're typing, and the monitor is probably displaying something on the graphic card, right? On the monitor, right? So things can run concurrently in this case, right? Now each device controller is in charge of a particular device type, right? So if you see, if you control alternate delete on your Windows system, you will see all the devices, and the devices are actually you can see all the connected controllers on your device list, right? and if we and each device controller has a local buffer by itself, right? So it has, as the disk is trying to as the disk controller tries to save stuff on the disk, it does have a local buffer to keep data and information, right? Similar with the USB controller or graphic adapter, right? So the keyboard and mouse, as you are entering input, there is a buffer that keeps that input and data before pushing it into memory, right? Or whenever data comes in from memory, it is kept into the buffer first before it's being displayed into the monitor, for example, right? All right. So the CPU basically moves data from and to main memory, or to or from local buffers, right? So is it is keeping memory inside moving data to the memory or getting data from the memory, or reading it straight from the controller's buffer right here, right? So you consider that all of this controller has its own somewhat like mini memory in it, right? So I/O is from the device to a local buffer of controller, and device controller informs the CPU that it has finished its operation by causing an interrupt, right? So whenever we're reading this, for example, and it's time for the CPU to get those data, the disk controller will inform the CPU via an interrupt, for example, right? Okay, so let's look at that. Now interrupt basically transfers the control to the interrupt service routine, right? And through the interrupt vector, which contains the addresses of all the service routines. So when an interrupt occurs, it needs to run code that the CPU would understand, and all of this is contained in basically a interrupt vector which contains the addresses of those routines, right? So we call that routines. The routine would be a specific code to run, right? Now, interrupt architecture must save the address of the interrupt instructions, right? So the address is where to find the routine particularly, right? A different type of interrupt, which is a software-generated interrupt, is basically called a trap, or an exception, and it exists by it happens because whenever there's an error or a user request from a software, right, basically, right? An operating system is basically overall interrupt driven, right? So okay, here's an interrupt timeline. So you see a user program running, right? Now the IO device might be idle and there's an IO request. This could be, for example, keying, your mouse moving, or you're typing something on the keyboard, and when it's time to transfer those, the interrupt will occur, right? So it will try to transfer, putting it in a bus, interrupt its signal, and the CPU stops from running the user program and process those interrupt, right? After it's finished interrupt, it will continue running the user program, right? And the disk will also continue being idle or until it receives some other IO request, right? So let's continue. Yeah. Interrupt handling on the operating system. The operating system preserves the state of the CPU by storing the registers and the program counters, right? So what this means is that whenever if you notice in this picture, we're running a user program, right? So whenever we're running a user program, that means, there's particular code that's running on the CPU already, right? That means the registers and the program counters is already set to a certain value to run this user program, right? Now, whenever an interrupt occurs, it has to be handled, and the current program right now, if we jump to handle a specific routine, and what happens to the user program and the state that it was before. So in order to preserve this state, right, so that it can come back here without noticing any differences, it has to preserve all the state that was occurring before it jumps into interrupt, right? So basically, one of the operating system job is also to make sure that everything that's stored in the register and the program counter is basically preserved, right? It will also determine which type of interrupt has occurred and separate the segments of code, determine what action should be taken for each type of interrupt. So it knows if what kind of interrupt it needs to run based on the code of who gives the interrupt and etc., right? So an interrupt drive IO cycle basically is such a way we have a device driver initiates an IO, right? And the IO controller basically initiates the input output, and when the input is ready, and it will try to produce the output or generate an interrupt signal, right? And when the CPU receives this interrupt, it transfers the control to the interrupt handler, and the interrupt handler would process the data from the interrupt, and after doing that, the CPU resumes processing of the interrupt task, uh, resumes processing of the interrupted task, so the task that was previously running, and continue, right, until it receives another uh, uh, interrupt from the device driver, right? Okay, right. There's two methods of IO structures, right? Of handling IO is that the control returns to the user program only upon IO completion, or the control returns to the user program without waiting for the IO completion, right? So in terms of when the first case, control returns to the user program only upon IO completion. This case, it waits the instructions to idle the CPU until the next interrupt. So there is a wait loop contention for memory access basically, and at most one IO request is outstanding at the time, and there's no simultaneous IO processing, right? So it kind of waits for instruction uh, to handle the next interrupt. But for control returns to the user program without waiting for IO completion, then there is a system call that requests to the OS to allow the user to wait for IO completion, right? So this requires more involved through a system call. All right, so we'll stop there. We'll continue in storage structure in a bit, and we'll come back discussing about what kind of storage is available on the common hardware computer, and how the operating system basically manages those, right? So I'll see you in a bit.